Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Utility substations are filled with equipment performing various functions to keep power flowing to homes and businesses. They contain a mix of old and new, analog and digital, simple and complex technologies, often from different manufacturers. What if managing devices for protection, control, and monitoring could shift from requiring many different individual devices to a single central processing unit within the substation? In this episode, I'll talk with SEL Chief Technology Officer, Dr. Greg Zweigle, about the concept of centralized protection and control and how it is transforming and improving electric power systems. Greg joined SEL in 1998. He held a variety of roles in the Research and Development Division related to the development of protective relays, signal processing, software, and programmable integrated circuits. As Chief Technology Officer, he fosters the development of innovative technologies and works in collaboration with executives and technical leads to set the technical direction of SEL. Greg earned a bachelor's degree in physics from Northwest Nazarene University, a master's degree in chemistry, a master's degree in electrical engineering, and a PhD in electrical engineering and computer science from Washington State University. He has authored and co-authored more than 35 technical papers and holds 32 patents. He serves as the chair of Washington State University School of Electrical and Computer Science Executive Council and is a senior member of the IEEE. Hi, Greg. Thanks for taking time to come back on the podcast.
Excited to be here.
This is going to be a fun one. There's been a lot of buzz these days on CPC, Centralized Protection and Control. Before we get into details, we may have some listeners who are not familiar with protection systems and how protection systems are deployed today in substations. Can you share the background of technologies today for protecting power systems?
Sure. So let me start with the substation. So I suppose listeners have probably seen a substation before. It's a fenced-in area with a lot of power lines going in and out of it. Maybe you've driven by one. And in a substation, you can think of it as a connection point in the power system. So a typical substation has high voltage lines going into it and high voltage lines going out of it. So for example, you might have 138,000 volts going into a substation and say 13,800 volts coming out of a substation. So that's a lot of voltage. And what transforms that voltage level is a transformer, interestingly, good name. And so a transformer will convert the voltage levels. And transformers are large pieces of equipment in a substation, and they're typically very expensive. In a substation, I guess the question then becomes, what happens if something goes wrong? Because we're dealing with high voltages, we're dealing with a lot of energy. And we need something that can protect the system, say disconnect the line if anything goes wrong. So, for example, if a tree falls on a line 30 miles out from the substation, or if a piece of equipment fails, right? So what do we do? And the answer to that is a breaker. So in a substation, in addition to transformer, is a circuit breaker. And that also is a very large, very expensive piece of equipment because interrupting the flow of energy, since we're dealing with really high amounts of energy, it requires some pretty serious power to disconnect that. So then the next question is, well, what tells the breaker to do its job? And that is the role of a protective relay. So the protective relay in a substation, it measures voltages and currents in the substation, and then it makes a decision on whether or not the breaker should open based on if the relay detects something failed. I use the word relay, but really what it is it's a real-time embedded computer, high-performance embedded computer. And so it makes the decision on whether the breaker should open the flow of current. So then when we talk about CPC, what we're talking about is a specific architecture for the protective relay.
Well, let's go back real quick, maybe a little bit of clarification for our listeners. I like what you said. I think the way I explain this to my mom is For simplistic purposes, the power system consists of about 3 different types of things. We have lines, we have transformers, and we have buses. And the buses connect the various lines together through some circuit breakers. And the circuit breakers are like switches in your house. They turn on and off the flow of electricity to, say, the lights, if we're talking about the switch. And historically, what we've done in the power system, well, I have a line to protect. So I'll get a box that does that protection of the line. And then I have a transformer inside the substation. So I'll put another box, that controls or monitors the transformer. If there's a problem with it, it'll send the signals out to the circuit breakers to isolate that part of the power system. And similar with the bus, there'll be a particular relay that's its only function is to take care of the bus. And that's all it does, regardless of how many lines come into the substation or how many transformers are in the substation.
Yeah, that's exactly right.
Okay. I think this is where you're headed. What is different about what we've historically done for the last, let's call it 40 years with microprocessor-based relays, and now what we're talking about with CPC?
Yeah, so that's good. Let's get into that part of the conversation since that's what we're here. And as you noted, we're talking about centralized protection and control. And so the connection to what we're talking about is that protection part, and we're talking about protective relays. So to understand CPC, I think we really have to go back to the earlier days of protective relaying, which is the early 1900s when they were electromechanical. Okay. So let me explain quickly how the electromechanical relay works, because I think that's a good way to understand where we're headed with CPC. So what they do is we need to measure the voltages and the currents in the substation in order to make those decisions. So we will have, say, 138,000 volt line coming in. We put a transformer on it and we lower that voltage to a lower level, like say 100 volts or something. Okay. And then that voltage gets sent over a cable from the sensor in the substation to there's a control house. And that's where the electromechanical relay lives. Okay. And like I said, if a listener has driven by a substation, they might notice it can be fairly large. Some are small, but some can be quite large. So that cable runs a fair distance from the sensor to the control house where the electromechanical relay is. And similarly, we need to measure the current. So, the current coming in and out of a substation could be several hundred amps. And so we have another transformer that will convert the current to a lower level, like say a few amps. And that goes over a cable into the control house where the electromechanical relay is. And so the electromechanical relay takes those signals, we call them analog signals because they're like a continuous waveform. And then, they're very sophisticated devices. They're based on electromagnetics and they have induction coils and a lot of moving parts.
Yeah,
right?
They're mechanical marvels.
Yeah. They're amazing devices. And that's how the decision on whether or not to trip that circuit breaker was done starting from the early 1900s until about the 1980s. In the 1980s, Dr. Schweitzer started Schweitzer Engineering Laboratories and invented and released what I would say is the world's first production digital protective relay. So when I said earlier that a protective relay is actually a computer, I was referring to that architecture, which is it being built on a computer. And what's interesting is it was a transformation of the technology, but that basic architecture didn't change. So the same, an electromechanical relay needed to have those voltages and those currents sent to it. The digital protective relay, which I said was a computer, but it's more than a computer. It kept those same analog signals, except it needed to convert them to a number because inside of the digital protective relay is basically a computer. So if someone grabbed a modern day digital protective relay and they lifted it up, it's fairly heavy because there's a lot of electronics in there to convert the analog signal to a digital signal. We call that an analog to digital converter. So we take that number and then we run that into the computer. So that architecture didn't really change when the digital protective relay was invented and produced. And that's the architecture that we've been carrying with us to this day. So now if we think about what CPC is, let's take a progression of thought. What if we took that conversion from an analog signal to a number and we moved it out to the sensor? So instead of taking 138,000 volts, lower it to 100 volts, run it over a cable to the control house. What if we converted that to a number at the sensor, and then instead of having a cable run across the substation, we had a fiber optic line. And that fiber optic line went to the computer. And so I've moved that conversion point out. So if we do that for the currents and for the voltages, now what that digital protective relay, which I said was a computer, and then I said, well, it's not quite a computer. It also has a lot of electronics. Now it truly is a computer, okay? So that's kind of the first step of CPC, is moving that conversion point out to the yard. And then we look at that and we think, all I have now is numbers coming into this box, so I can get rid of all that conversion. And it, like I said, it truly is a computer. And now I can merge them together. So earlier you were saying there's one digital protective relay that more or less looks after the transformer, one that more or less looks after the outgoing line, the incoming line. But now, since it's just compute, I can put that all into one box. So I can put one big, gigantic, 10-foot tall computer in there, put it all in one location. So that's why we call it centralized protection and control. So now we kind of have the acronym. It's protection because it's doing the function of looking at the analog voltages and currents and converting them and deciding whether to open the breaker. And it's centralized because I put it all into one big, gigantic computer.
I like the way you described it. I have a slightly different way of thinking about CPC and the motivations for it. It's because back in the day when Ed was coming up with the 21 relay, he had a 2 megahertz microprocessor, and he had to get very clever how he did those computations that you were just describing, because he just didn't have enough CPU cycles in the allotted time for protecting a power system to do much more than what he did. Fast forward 40 years today is we got lots of fast processors, lots of computational capabilities. And so you can start asking yourself, since I have all that computational capability, could I just replicate as many 21 relays as I need in this box? And then the answer is, yeah, you can with this new computation. Then you start scratching your head as the hardware engineers to bring in all those analog quantities. Like you said, this box would probably be bigger than a refrigerator. And so to limit the size that you have to put inside the substation, to your point, why don't you just put those data acquisition units, the things that are measuring the currents and voltages, really close to where those measurement points are on the power system, and then just bring it in through a fiber or a cable or something like that to this much, much smaller now computational box that's doing a lot of that protection, whether it's lines, transformers, or buses.
Yeah, and actually, to that point, it's kind of interesting because some people will ask, well, is CPC new or what's different about it, right?
That was going to be my next question.
Oh, was it?
Yeah.
Okay. Well, I can go right into it if you want.
Let's do it.
All right. So, yeah, I've described it so far. We've described it so far as these kind of discontinuous steps. First, there was electromechanical, then this discontinuous step, then there's a digital protective relay, then this discontinuous step, then CPC. And that's not really how it's progressed. As you mentioned, the early days of the digital protective relay, it had limited compute, so it could only do so much. Now, as compute is the capability to do more and more with the processors we have, over the years, as an industry, we've been integrating more and more into that digital protective relay. So what today is, for example, an SCL 421 is so different than what was built back in the 1980s. So we've been integrating over the years more and more functionality into these devices. And I'd say CPC is in many ways a progression of the further levels of integration because we have more compute power.
Yeah, even Ed's first relay, where it was an integration, perhaps the first step in CPC. Because if you go look at a panel lineup back in the day, there'd be one relay for the A phase, one relay for the B phase, one relay for the C phase. And Ed was, even though he only had 2 megahertz of computational power, was able to take those 3 phases and do all the computation and protection inside that 21. And then to your point is our ability with even more computational power 20 years later, we can get rid of more and more of these boxes you saw in older panels and start condensing them into single boxes.
Yeah, exactly. Because those were electromechanical relays. And so they were kind of stuck, right? They did one per phase. And that was an early, as you noted, an early level of integration to pull those together into one device.
So sometimes we say just because you can do something doesn't mean you should do something. What are the benefits of a CPC system? Why would somebody trying to protect the power system, keep the lights on, gravitate to putting all your eggs into one basket? Let's put it that way.
No, I mean, that's a great question, because I think if I was a listener listening to this, I might be thinking, okay, you move this here, you move that there, you put this, it feels like we're just kind of moving stuff around, move stuff around. What is the point? And there's a couple things. One, as we were talking about earlier, the way things have always been done and are done today with the measurement at the sensor and then brought to the control house over a cable, that's a lot of cable. And that's a lot of copper. So the thinking is, well, if I can replace that with a fiber optic line, that can significantly reduce the cost of that connection. Now, I would say maybe it could reduce the cost of that connection because there's some complexity, and we'll probably get into that a little bit more later. So that's one potential advantage. Another one is flexibility. So once I have a computer that's that's these algorithms centralized. Now, by the way, I described it as one big, gigantic 10-foot computer. In actuality, that's not exactly how we build them, right? We can do a lot of different things for scale. We can do things for redundancy. So there's typically multiple of these computers. But once we've got the algorithms in software on a computer, now it's software. So I can have a lot more flexibility in terms of the control, the protection, what kinds of algorithms I am putting into that device. And what's interesting is if you think historically, that level of flexibility probably would not have been viewed as an advantage because power systems for many decades were, we have base generation, nuclear coal. It runs fairly unidirectional. It goes down a distribution line. It goes to someone's house or a factory. So is the flexibility really needed? But what's interesting is the ideas of CPC are coming along right when flexibility is becoming a lot more valued because the power system is changing so much, right? With wind and solar and electric vehicles, batteries, we have different ways to do markets. There's just a lot of things, data centers. I mean, I could go on and on. So there's a lot of change right now and a lot of utilities, and I'll speak for the utilities. I think they might be thinking, okay, once I put this substation into service, I've built it, I've commissioned it, I don't really have the people or the time to go back and redo this thing in 5 years. So the nice thing about CPC is it gives potential flexibility because now the algorithms are in software. And with the changes in the power system, that amount of flexibility is something that becomes more valued. Now, there's a couple more I'll mention really quickly. One is the potential for safety improvements for the people that work in a substation. So even though we were talking about hundreds of volts and, a few amps going to that control house, still we're asking people to work around voltages and currents. And if we do all that conversion out in the yard and bring it across digitally, now that control house in the substation, it looks like a lot of computers and racks. And so there's a safety challenge improvement. And I'll mention one more, which is, and this one I would say also is a potential. It's a maybe, but there's certainly the opportunity, which is to reduce cost and complexity. So now I've potentially simplified things by bringing everything into centralized computers and running everything with software. But I think hopefully in this discussion, we'll talk about some of the challenges of CPC, and this is going to wind up on the challenge list as well.
Earlier in this conversation, we talked about lots and lots of relays, especially if you have a large substation for doing all this protection, which I just think from a maintenance standpoint is I have to worry about the cybersecurity in each one of those individual boxes. If there's a firmware upgrade, I have to go touch a bunch of different relays to get it to the latest version of firmware. One of the compelling arguments for CPC is reducing your cybersecurity footprint because now I'm guarding one port, not 10 or 20 or 50 or 100 different cybersecurity ports or threats. I'm managing one set of firmware and the ability to potentially scale the system. I built a substation with 5 feeders and there's another data center that comes in. So I have to put in another line and transform. I should be easily able to, from a software perspective, put those features and functions in without really having to change the hardware that's inside the substation.
Yeah, I agree. And what's interesting, since we're talking on this path about software, I say it has its pros and cons. So,
let's talk about challenges now, right? Let's go down that road.
All right. Yeah. Because it's hard for me not to start thinking about the challenges of the software. Yeah. Well, I'll start with that one. So software is interesting. And at SEL, we've got this really high value on simplicity. And software, yes, it can make things potentially simpler, reduces the device count. But I view software as it's a technology that must be used with great caution. And sometimes I worry that as a world, we get so familiar with software that we sometimes forget that it is something that, we need to use with great care. I think about it a little bit like a piece of heavy machinery at a job site, which, it's great because it brings a lot of advantages, but for safety, we always have to understand what we're using. We have to be careful not to get complacent. So software has the advantages, like you mentioned, but it also brings its own cybersecurity challenges with it. And when not developed properly or carefully, sometimes those software stacks can get really large. It can bring a lot of additional software into the protection and control path that wasn't there before. And that can cause lots of things. It can cause reliability issues. It can cause cybersecurity issues. Sometimes I like to joke that I feel sometimes our world says that the solution to cybersecurity is more software, when in fact software is a lot of times the challenges with cybersecurity, right? Because each new line of code brings the potential for an attack or a bug. So I think that's one of the potential challenges with CPC. It's like there's upside and there's downside. There's pros and cons to it. And the other thing too that I think we have to think about when it comes to CPC is going back to that network. And I described earlier, and I said, well, we replace all those cables with a fiber optic line. And of course, and probably our listeners know, I really simplified things when I said that, because that's not at all how we do it, or at least how the industry has been talking about doing it. Instead, it is a fiber optic line and a network, and a switch and a clock. And so I've taken what used to be a wire, effectively, from the sensor to the protective relay, which is super simple, and it moves that signal fast, speed of light, basically. And I replaced that with switches and clocks and power supplies and a network. And so, I think that also is a factor when it comes to CPC, is making sure that we can do that reliably and also fast. I haven't mentioned speed yet when it comes to protection, but that's super important because we're talking about something that's protecting lines, it's protecting against damage to equipment, and speed is really critical when it comes to protection. And so,
just to clarify too, right? We talk about cables and networks and switches and whatnot. I'll make an argument that while we have separated those things, it's not the network, it's not the cables necessarily that are going to slow down the protection. It's probably the processing rate of the algorithms for the protection will be the limiting factor, and the fact that we've now made the processing have to happen in two different spots. One out at the device we call typically merging units that are measuring currents and voltages. They have to digitize it, packetize all the information up, then send it to a very quick network, I am sure. The other end has to receive it, decode it, and then make the decision to trip or not trip the breaker. And then, it's got to packetize that information back up, send it back out through the network to the merging unit to go ahead and trip the breaker.
Yeah, you've got it exactly right. I was kind of simplifying things, but yes, that entire path, that entire data path adds more software, more potential latency, more potential for things to fail versus a cable.
Oh, yeah.
Right. So
and one processing element.
Yeah, and one processing element. But I would say it's not, I wouldn't want to say that this is a showstopper or to give that impression. I think what it is that our industry, I've noticed, and I'm very impressed with, has been moving forward with this very methodically and carefully, right? We see, well, certainly at SEL and at utilities, they're putting these things into labs, they're putting them into pilots, they're very carefully moving forward with this, which makes a lot of sense because we have an architecture that's been in place since the early 1900s, right? And it's been proven in the field over years and decades to be reliable, to be safe, to be something that we can count on. And so now we're making some pretty significant architectural changes, and as engineers, we are doing so methodically and carefully. And I think that's very important just because of how critical the electric power system is, and it needs to work.
Yeah, Ed reminds us all the time the power system is not a lab.
Yeah, exactly.
Okay, here's the next question. We talked a lot about CPC, but there's also something out there called virtualized protection and control. Would you describe the differences between them? And what are the advantages and disadvantages between CPC and virtualization?
Yeah, that's a great question. And it's interesting because a lot of times, like if I just heard this for the first time, and maybe a listener is hearing this for the first time, they might think, why are these two concepts even coupled, right? But a lot of times in our industry, they're actually CPC and virtualization are used in the same sentence. So that's interesting. if you go on the internet and you search for what is virtualization, the typical definition is something like virtualization is a technology that lets us use virtual computing environments, right? It's really, I don't find it super helpful. But in the world of CPC, what this means is that the concept of separating the hardware from the software. So as I described, the way you described actually the digital protective relay, where it was each is protecting a specific element of the power system. Today, those are shipped with the software. We call it firmware if it's in a real-time environment. And the hardware are designed, engineered, tested together as a unit, right? And that's because it's so important that this just works. We look at, now I put this in a computer, people are starting to think, well, I could separate the software from the hardware, and then I can treat them separately. And so that's the concept of virtualization. And, maybe one way to think about it is like a car. So, today a modern car has a lot of software in it. The hardware is the engine, the wheels, the tires, the steering wheel, et cetera. And the software is the in-car entertainment and the engine controls. And so maybe someone would think, well, why don't I buy a car and then I buy the software separately, and I can make that car be a lot of different things with that software. And so that's kind of the idea. And of course, there's a trade-off, because maybe I just want to buy the car and have the manufacturer make sure that that all works reliably. And so that's the thinking of CPC and virtualization. And there's a lot of research going on in this area right now and a lot of different ideas. So it's kind of exciting as an engineer, but I say that there's still work to do to figure out what exactly that looks like. At SCL, we have a virtualization technology. It's called BlueFrame, and that goes along the path of delivering the hardware and the firmware together. So we, of course, with that solution, we test it all together as one integrated system. And that way, when we deliver it, we know it's going to work. But the cool thing is it gets some of the advantages of virtualization because it's much more flexible and adaptable to a lot of different environments.
We also have a little bit of history when you talk about virtualization with our software-defined networking technology, where we've really abstracted the network hardware, the switch hardware from the software. And so to your point, we have a software package that will go ahead and program all the flows and nuances of networking down into the hardware. And then you can actually pull the software totally out of the system, and the hardware will continue to run as it's programmed. And the way we've also designed it using some open standards, OpenFlow being the standard, you could actually have somebody else come in and program our switch to do the various functions. I think that what maybe you were headed this way with the virtualization side of it is that what we don't do with these particular systems is, okay, you set up the switching fabric with one set of software, and then, the time distribution through the Ethernet switch or the SDN switch is done by another set of hardware. Rather, one set of software takes care of all of the programming of the hardware, as opposed to perhaps mixing and matching, which I think is some of the objectives of the virtualization aspect of CPC.
Yeah. And actually, when you mentioned that, it reminded me of something else. SCL's done a lot of innovation when it comes to that network side with SDN, like you mentioned. The other thing I'd like to mention really quickly, and maybe to clarify something, because if a listener is not super familiar with networks, they might be thinking, well, wait a minute. Originally, you said I'll replace a cable with a copper cable with a fiber optic line. And then later on, I said, well, we need a switch and a clock. But someone might be thinking, well, why do you need that? Why can't you just run a fiber optic cable? And it turns out we've done that as well. We have a technology called Tidal, where we basically replaced each of those cables with a fiber optic line, just direct connected. So there's some advantages to that, because it's simplified and eliminated some of that network complexity, but also got some of the advantages of being able to move the sensors out to the actual equipment.
And just to be clear, when we replace a bunch of copper cables with a single fiber optic cable, because we can run all that information through that copper.
Yeah, exactly.
So there's a lot of reduction of cables, whether they're copper or reducing a lot of copper cables with a single fiber going to and from the substation into the control house.
Yeah, exactly. We didn't take one A-phase current cable and replace it with one fiber optic line and so forth like that.
All right. So we've talked about CPC. We've talked about virtualization. Where do you see the future of this? Because certainly there's a lot of little trials going on. with different ideas of how to deploy stuff. Because technology is one thing; it's how does a customer buy something, deploy it, maintain it, support it for years and years and years. And there's still a lot of work in this area to get done. But where do you see the future of centralized protection and virtualized protection?
Well, I would say first, our industry is still very much in methodical engineering phase in all of this. And I really appreciate that and have a lot of respect for that. We've been doing several different things. For example, we took our SCL 487E, and I don't want to go into too much detail on specific things like that, but we've made that into a CPC as a step where utilities can really use protection equipment they're very, very familiar with and is very proven, but then bring in some of the CPC concepts. We see, like you said, a lot of pilots going on. There's a lot of research going on here at SCL. And I think what would be kind of fun is maybe to do a round 2 of this podcast sometime and look at, okay, now that we've kind of outlined the basics of the technology and some of the history, what are some of the details of the projects and the things that we're working on at SCL?
Greg, we've talked a lot about the benefits of CPC to the engineers and the folks operating the power system. What do you see as the benefits of CPC to the consumer, me and you at home when we're paying our electric rates?
Yeah, there's a couple of things I could think of. One is, I'll go back to that flexibility. So one of the things that is happening in our world is we want to continue to increase wind and solar and batteries and all these, electric vehicles, all these things that are changing about the power system. And utilities sometimes, like I mentioned, once a substation goes into service, it's hard to change it, right? It's already been commissioned. It's been built. I mean, they don't have a lot of people to go back and redo things. So that can potentially impede the progress of these other alternative energy sources. So with the flexibility of CPC, once that substation is there, now I can change the functionality with software as I need in order to integrate these other sources. So another potential advantage of CPC when it comes to how it impacts the end user is, as you had mentioned earlier, Dave, there's a lot of different devices in a substation today. You go into that control house I described, and we're going to see a wide variety, maybe, I don't know, how many protective relays you think there is in a typical control house, like 20 or something?
I don't know if there's a typical one. Certainly 20, 30, 40.
Yeah, there's a lot of
equipment. If it's a really big substation, yeah.
Yeah, there's a lot of equipment in there. And so there is a cost. There's an operational cost of managing that, managing the firmware, managing all the different devices. So we go to something that's a computer plus software. So that can really drive down their operational costs. And then that goes back into the cost of electricity or the price of electricity.
Well, and Greg, you talked about a bunch of the CPC projects we're going right now at distribution substations, a small number of feeders and whatnot. But I used to be a little bit skeptical about this CPC design, but as I look at the technology, the capabilities, things we've been doing with customers, I'm convinced in the not too distant future, distribution systems will be based on CPC just because of the speed, the flexibility. I think some of the complexity it saves asset owners from having to manage. I think there's a bright future for CPC, and I'll have you back on the show in a couple of years.
Cool. Sounds good. Thank you.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.